Okay, let's get started. Good morning, everyone. And this is E141, lecture 17. So I made it back from my trip from Intel, and I'd like to give you a brief report what's going on up there. So the big news this week is basically that they released this multi-core server processor with 1.76 billion transistors. Remember, Pentium 4 was about like 40 million transistors. It's almost 2 billion transistors. So it's the first uh, processor that goes with more than billion transistors, and also they are pretty excited about ramping up production line with 65 nanometer node. And where is this going forward is basically we will see more of this multi-core processing approach, because basically we are hitting the end of frequency scaling by improving performance, by improving our frequency, and also we can't scale supply voltage as aggressively as we did before because of all the variability issues and leakage issues. So we are kind of entering the regime from basically, and we can't also shorten the pipelines anymore because we are already at about like shallow pipeline stages, maybe 7 or 8 stages. So we basically are past the era a long time when we had just the pipelining approach. Then we also kind of transitioning now from the era where we had instruction level parallelism, and we are really now doing this multi-processor parallelism, processor level parallelism. So the frequency will level off. So when you look at the power issue, you have basically FCV squared. So frequency is constant, C is going to reduce a little bit, VDD squared is going to also reduce. So you end up having basically much less power due to scaling benefits. So you can add more cores next to each other, and then you also are solving this global communication problem. And this is where it's going to go in the future. And also you will be seeing much more of these things, that you add some dedicated hardware units, because the clear emphasis is on end user communication and computation needs. And so maybe 5 to 10 years from now, you will have your laptops with 16 processors. What you're going to do with these 16 processors, we don't know, but that's what you're going to be seeing more and more happening in the future. So maybe you will have to shut down 15 processors and use just one, and then basically improve your battery life on your laptop, and then you will be basically thinking back to the time when you took this class. Oh, that was the good old times when you had only one processor. Now look what we have in front of us. So that's the news. And are there any questions about the project? I assume you are now almost done. Everything going all right? You're done? Have you started? All right. So this week we will do some project help in the labs, and we got the email from these lab administration people. They're asking you to close the door behind you, so you don't leave the door prop open, because they have some security concerns about that. So please make sure that you close the door after you and use your card key. They are threatening us that they will disable card key access if we keep doors open after us. So please do close the door behind you. So a couple announcements for today. Project 1 is due on Monday, and we would like to receive reports in electronic form. You can send reports to this email address, e141@Cori, and also please include your SPICE deck, because we will most likely be running your SPICE decks and see if that corresponds to the numbers you got in your report question.
In the report template, it says to include a pointer to the SPICE deck.
The pointer basically means you can either give us location of your file where we have read permissions, or you can simply email it to us. So I guess just attach your SP file. It's not a big file, it's just a text file, so that will probably work the best for everyone. And we'll post homework 7 today. That will be due next week, and we'll give you a little break with labs and everything, so no labs next week. Any questions? Maybe I can give you a couple hints as an introduction to the lab today. and your spice verification. I got quite a number of emails from people, and I saw a discussion on the news group. How do you verify your results in spice? Because for the phase one, it's okay, it works out nicely, but for the phase two, you get huge discrepancy, and you don't know where it's coming from. So that's one of the reasons we gave you homework 6, problem 1. Make sure you really understand what's going on in that problem 1. But in general, when you have a design such as the one that you have in your project, and you have an input over here, and then you have outputs, then when you're looking at this design on a macro level, and basically you're only interested to see what's going to happen when I resize my design and then I measure these delays to all these 3 paths. Then I have some discrepancy from what I expected in my hand calculations. Now, so what you're supposed to learn from this project is basically how do you really track down where these discrepancies come from and understand what's really going on, so you can improve your design to meet your performance specs. And so obviously the next step you want to do is basically starting from this block level design. You want to go inside this box and do some probing at the next level of hierarchy below. So what you want to do is basically, okay, so now I have some discrepancy and some things that I don't understand. So let me see, basically, if I have the delay discrepancy, let me see where is this coming from. So it's really, next logical step would be to sort of understand the building blocks, to be basically the stages in your design, and then see how does the delay of these stages look like. So you basically take the delay of this individual stage and see if you have any discrepancy from what you would expect in your hand calculations. And then when you see where you have the most discrepancy, basically what is causing the discrepancy, you basically look at the fan out, you look at your signal waveforms and things like that to kind of try to figure out what's going on. And then you continue pushing down the hierarchy until you really figure out what's happening. So that's basically the methodology that you should be following and the way you should be thinking in trying to explain discrepancy and what's really going on. And you don't really need to re-optimize this in SPICE. If you do so, you will get an extra credit, but we are not asking you to do so because likely you will have some discrepancies. Then you can take a next step and basically say, well, this design in reality doesn't really meet the constraints that I'm imposing because I have too much slack. Maybe my delay is faster in SPICE than what I would predict, so I can really trim down the gate sizes even more. And that's what you're not required to do, but it's great if you do. So I hope you are all on the same page and clear about the methodology you need to do for the final phase. Any questions? All right, great. Question? Huh?
With respect to loading our inverters, should I heard this there's some difference between size 16 inverter and 16 size 1 inverters, and I was wondering what that difference was as far as the loading is concerned.
That's a great question. So the question here is, what's the difference between size 16 and 16 times unit size inverter? And that's basically when you think back of discussion we had a couple lectures back for the implementation of really wide transistors, when you have all these fingered approach and things like that, versus when you have all these just like parallel instances with a lot of contacts and things. So that is basically the difference in a physical implementation of the device that is 16 times wider versus the device that is 16 times the unit size. So what is the easiest to do and probably makes most practical sense for this project is just basically use the 16 times the unit size, because that's the model that we really calibrated. We calibrated gates that are 2 to 1, and then you use a couple of those in parallel. If you just really want to upsize and use 32 by 16 gate, then you're kind of changing assumptions about your model, and then you're sort of getting off track from your delay calculation by hand. And in reality, you really have like a discrete set of these inverters, and you have a library 1x, 2x, 4x, 8x, and then you combine everything using those. If you need more, you basically put them in parallel. And that's basically the approach that we advocate in this project. It's still not quite optimal. You would probably use 2 8x inverters in parallel, but just assume for this project you just basically deal with unit size inverter and then scale that up. Is that answer? Okay.
So then is that true for our other inverters in the chain as well? Like if we have an inverter in the chain, like in block A, that's size 20. Do we use 20 unit sized inverters or just one that's size 20?
You instantiate 20 unit size inverters. That's good. Just for the modeling perspective and sake of basically just getting the first order understanding of what's going on. It's more accurate, as I said, to break it down using the largest possible buffers that you have and then work with those numbers. But just for the purpose of understanding what's going on, you use the same model.
So from after optimization, if the values of y1, x1 that we get are not integral multiples of the unit size buffer, then what do we do?
That's also a great question. You can try to make them as close as possible to like this multiplication factor. So basically, if you have, let's say, Wn is equal to 1.8 times, if you end up with a sizing factor 1.8, then you just basically use the 1.8 factor. That's fine. It's not too big of a deviation. But if you end up, for example, with a sizing factor 2.2, then you can maybe instantiate two parallel inverters, each of which is 1.1 size. So try to sort of like get that approach with utilizing as close to unit size as possible. But it's also okay if you just upsize by a certain factor if it's not too large of a factor, because you're not going to end up with huge sizing factors. So that approach is also okay. Any other questions? Okay. So last time you heard a very detailed story about pass transistor logic, and today we are going to basically explore a couple more logic styles. And after next 2 or 3 lectures, you will be pretty much able to understand what's going on in these like multi-core devices when you have all these ALUs, processing elements and things, because basically the concepts that we are trying to teach you in this class will be expanded upward hierarchically, and you will soon understand how to do all of these kind of trade-offs and large-scale designs. So what you're going to do is basically today just finish our base of different logic styles that we are able to use, and so the next time you will hear about adder design, some arithmetic units, various styles of adders, architectures, and so on top of these circuit techniques, and then we will go into multipliers, ALUs, and so on, and then by the end of next week you will be able to get a sense of more of these system level issues. But in reality, we are really doing more of just simple concepts and just expanding them hierarchically and then coming back to all the old ideas that we've already introduced. So that's what we're going to continue today. As a recap from last time, here are some of the alternative logic styles that we introduced as potential replacement to static complementary CMOS. So the idea basically is that CMOS has this redundant P network, pull-up network, and that costs you a lot of area, and you don't necessarily want to deal with that. So the ideas came to explore how we can basically reduce that redundancy and overcome that problem of too large area in the implementation, and that's how people came with all these logic styles that have this underlying concept of reducing area. So it's basically, we looked into ratioed logic that had only pull-down devices and a fixed load. That one wasn't really good because you always have to sacrifice something when you make a trade-off. It's like in real life. So you have to basically, here you have a static power, you have reduced noise margin, but you have smaller area. So then we looked into DCVSL, which had differential outputs, and the problem was that you have double the wires and increased dynamic power. Again, this may be useful for some applications when you need differential signals, so we are going to explore more of these flavors. And finally, pass transistor logic, which was very attractive because it was modular. So you can implement a variety of gates by using identical layout structure. You just basically rearrange the signals. You can do AND, NAND, you can do XORs, same layout. But you need level restoration. You eventually lose the level of your signal as you go down the chain, and that wasn't really favorable property. And these are some of the guidelines. Static CMOS is getting used all over the place pretty much. This is the most conventional design style. And that's especially the case with the advancement of design automation tools, which basically are supporting this static CMOS style. With all these other logic styles that you're talking about, it's not so clear how to do them, because you are having problems with reduced noise margins, your design complexity is getting higher, you have more noise contamination, and you have to do a very careful job if you do use some of those techniques. All right. So finally, dynamic logic. So this should be a really exciting topic to learn. So this is basically the same underlying idea. In static CMOS, we know that we can implement a function using two N devices. N devices are NMOS, and N devices are PMOS. And some of the good properties of static gates are, that we remember, is that you really have a well-defined logic levels. You have ground for VOL, you have VDD for VOH, and you have very low impedance zeros and ones, which is really good from the noise standpoint. Now, what's different in dynamic circuits is that they rely on temporary storage of information on a high impedance node, and that's going to be clear in a moment. I'm just giving you the high level introduction here. And that's basically, you're trying to store your logic zeros and ones on a capacitor that is not necessarily always connected through a conducting device to VDD or ground. It's basically just you leave some charge and then say, all right, now it's your job to keep it. And the good property of these gates is, again, reduced area. You have N plus 2 devices. And let me show you now what the basic principle behind dynamic gate. So in dynamic gate, what you have is the following. So the idea is to also implement this pull-down network, but in a slightly different way. So in dynamic logic, unlike ratioed logic, what we are trying to do is basically eliminate static power consumption and eliminate this ratio problem, that our VOL depends on the sizing ratio of the PMOS and NMOS. So to do so, here's an idea. Okay. So let's assume that I have this PMOS device over here, and that I have a clock signal. So what this means is basically that if I have a clock signal, phi, this is what I'm going to have. So what this does, when the clock is low, I'm conditionally pre-charging this output Y to logic 1. And then, when my clock is high, then I can conditionally discharge this pull-down network. So you're really operating in two phases. So you have, first phase is pre-charge. So phase 1 is pre-charge, and that's where you are charging up this capacitance over here when this node is being charged up by PMOS, and this is your load capacitance over here. So on this waveform, time waveform over here, you have pre-charge over here. So you see what's going on here? So you're basically wasting half of your time that you could use otherwise for computation. So you can basically only set your logic level at during this time when you can conditionally discharge. Now, what's happening in this other phase? So this transistor is on. So then you have discharge phase. And this actually corresponds to your evaluation. You evaluate your logic function during these times. So you have only certain period of time where you can evaluate. Then you can't do anything here, can't do anything. So you can evaluate and oops. So you have evaluate, 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 and then you have this period of time when you can't do anything. And in reality, this may work well, actually, in some applications when, for example, you have you can coincide your instruction decoding with pre-charge operation. Then it works okay. And then once you finish instruction decoding, you can simply evaluate your function. And then in these certain scenarios, it works. But it's very important to understand here is that your output is now a function of time. So in static CMOS, we had really just like a static operation. You set some logic value, you have output. You can wait infinitely long, you still have basically that output. But over here, you really need to make up your mind. There's like, okay, I'm giving you this signal quick. What do you want to do? Nothing? All right, you have to wait now, and so on. So another caveat here is that once you decide to discharge this capacitance by setting some of these inputs to 1, then if you change your mind during this evaluation period, too bad. You cannot charge it up again, right? So you have only this phase 1 pre-charge when you can charge it up, and you have only this other phase for evaluation when you can only pull it down once. And if you change your mind, wait until the next cycle when you become pre-charged again. Is that clear to everybody? Okay. And let me show you one example over here if you go to slides. So this is an example that implements a function a, b, or c. So you basically now just do this simple pull-down implementation. You have a, b in series in parallel with c, and then you have this conditional discharge. So the phases go as follows. So basically you have the pre-charge phase, which is given in red. And in this particular set of slides, I'm using the color code. Red is bad, blue is good. And that's going to propagate through the rest of these slides, just to give you a flavor. So basically, you're pre-charging this one first because you're not doing anything useful. But it's in essence, it's a neat idea because sometimes your function is really at logic 1. And then you're saying, all right, while I'm doing instruction fetch and other things, let me pre-compute. And I'm guessing, oh, it's 1. So how about that? If it's 1, great. What's my propagation delay, TP LH? If you start from the evaluate phase, it's 0. That's great, right? I already have the value that I want. But if it's not the case, then I need to discharge and provide the correct logic value. So in the pre-charge phase, MP is on and ME is off, and you have logic 1. So when you evaluate, pre-charge device is turned off, evaluate device is turned on, and then you enable this pull-down logic network. Now, the value of your output over here is equal to basically AB plus C bar, but this is conditioned with this clock signal now. So when the clock is high, only at that point you have your output equal to AB or C bar. When the clock is low, your output is always equal to 1. Okay? So this is basically an additional term that corresponds to this pre-charge operation. So your output is equal to this pre-charge, which implements logic 1, and this evaluate term that implements logic 0. Okay? So let's now go to slides over here because we have go to overhead. Sorry, thanks. So we can illustrate this using the picture. So as we mentioned, once the output is discharged, it cannot be charged again until the next pre-charge stage. You can make at most one transition. And now let's assume that you basically pre-charge your device, and then your logic value that you expect at the output during the evaluation phase is still equal to 1. So what you have in this case is basically this situation. So you have your capacitance that is initially pre-charged. This transistor is turned off. Pull down is also turned off, and you have this node floating. So you have really high impedance, and this is very sensitive to noise. If you have, for example, another line that's running through here, and you have some capacitance, capacitive crosstalk, and then if you're trying to maintain your logic level 1 here, but these guys are sort of doing some vigorous activities, then you may have some charge coupling, and then this node will become contaminated because it doesn't have low impedance path to VDD or ground. So now some more properties are basically, it's always interesting to see what's the transistor count for the implementation, because we know the benchmark case is standard static complementary CMOS uses 2 N devices. So in this case we have basically N devices for the pull down. We have 1 device here and 1 device here, so we have N plus 2 devices, which gives us a good area with respect to complementary CMOS. We also have full swing output, VDD and ground are equal to VOH and VOL. And unlike ratioed logic, these voltage levels do not depend on the pull up and pull down of the PMOS and NMOS. So it's non-ratioed because sizing of the devices does not affect logic levels. So now this is about like DC parameters to a first order. And notice that in this case, actually, you can't really define your DC properties and voltage transfer characteristic, because this is kind of a pathological case in a sense that this device is dynamic by default. So it doesn't really exhibit static behavior because you always need to toggle this clock to provide correct operation. So really your voltage levels depend on the time as well. So when you look at your VTC stuff, then you really have to take into account this time perspective, because you don't have infinite amount of time to settle with your logic level. So what is going to happen then is you basically have, depending on how much overdrive you have on the pull-down network, you have your final output voltage level at certain value depending on how much time you give it. And that's, let me just clarify that a little bit here. So what you have is, so let's say this is your pre-charge, this is your evaluate, and this is your evaluate. So now let's assume that, for example, in the evaluate phase, you have this pull-down network, and you're changing this voltage level over here, just like you do for the standard VTC type of analysis. And then you have this evaluate device, and you have this pre-charge device. So in this case, you basically start the evaluation phase from VDD. That is where my capacitance is pre-charged at the end of this pre-charge phase. So when I start at VDD, then depending on how much overdrive I have, then I'll basically start pulling down this node. And at this point, where I need to pre-charge again, then I basically have certain value of the output. The more of the overdrive I have, the more I'm going to pull down. But there is no guarantee really that I'm going to pull down all the way to 0. So what you do in this case, you can basically assume and make approximations that your VIH is approximately equal to VTN, because that is where your pull-down network really turns on. And you can also assume that that is about where your switching threshold is, because you no longer have this situation when you have your pull-up network conducting at the same time, so you can really establish V in is equal to Vm, and that is equal to V out. That's no longer true, because if you apply some overdrive over this VTN, what's going to happen that your output is going to be slowly discharged to a final value, and now it just depends what's your clock frequency, how much time you give it to discharge. So it's basically from this time dependency, you basically just say, let me assume that my switching threshold Vm is also approximately equal to Vtn, just like VIH is. This would be VIL, sorry, because that's the lowest voltage you can still treat as logic 0. So now what does this mean for the noise margin? That means very poor noise margin for logic 0, right? Because you don't have much margin over, because this is much less than VDD over 2. So you're really tightening down your logic 0. And that is the biggest drawback, one of the biggest drawbacks of this dynamic implementation. And but there is also some good things. Unlike static CMOS inverter, this capacitance is reduced because you have fewer devices connected to the output, and also the size of this PMOS, we will come back to that later, has to be fairly small because you have really half of the clock period to pre-charge. So it doesn't have to be really big, and we will see some other issues that will basically determine precisely what would be the sizing ratio of this pull-up device. But anyway, it introduces very little capacitance. And you have reduced overall total capacitance at the output. And the other thing is you don't have short circuit power. So this is even better than the static CMOS because you're no longer fighting your pull up and pull down at the same time, because for the pull down, for the evaluation, I'm already pre-charged. So the PMOS is done and cut off by the time you start your evaluation. So all you're doing is basically scratch this off, and this is your evaluation phase. You just have this high impedance node that you need to eventually pull down if conditions for pulling down work out well. So that gives you some really favorable properties. But now, how about power consumption? Would you expect power of this dynamic gate to be higher or lower than the static CMOS? So you have all these nice things that you have reduced capacitance and such, no short circuit power, but power is still significantly higher. That's the problem here. And let's illustrate that. So let's analyze the simple case. Static CMOS inverter over here. Let's say this is A, this is Y, and let's do the dynamic implementation of the same inverter over here. So what you have now is you have this pre-charge device, then you have output, and then I have my pull down, and then I have this conditional discharge. So now let me assume that this input A is equal to 1. So output Y is equal to 0. So looking over time, what's going to happen in this static CMOS inverter? So my A is equal to 1 and Y is equal to 0. So no switching power is equal to 0, right? It's equal to leakage, but let's just ignore leakage for the moment. So now let's look at this guy here. So let's do the dynamic. So first of all, we have this clock. So what's going to happen is that this output Y is going to be pre-charged to logic 1 every time you have pre-charge phase. But now, since A is equal to 1, what I'm going to have, every time I can evaluate, I'm going to do so. So basically I have a lot of switching power. Right? Everybody clear with this? So basically, this is one of the main properties of dynamic gate. And that is that switching probability at the output of a dynamic gate is much higher than in a static gate. And we will come to analyze this in much more detail when we talk about the power consumption in CMOS gates when we go across all of these logic families and then calculate switching probabilities. But for the time being, this is just what you need to remember. Now, there is also another case. Then you can basically say, well, let me assume that my A is equal to 0 and Y is equal to 1. Then in this case, if A is equal to 0, you will never basically pull down, and again, you will stay always at this precharge value. But there is also, and in that case, the power is comparable. But on average, when you look at the signal statistics, you will end up with much higher switching probability. And just to give you a sneak preview of what's going to be discussed in a couple lectures in the future, is that basically the switching probability of 0 to 1 will be equal to the probability that your output is equal to 0. Simple as that. And that is always higher than P0 times P1 that you normally find in your static CMOS gates. That's the reason. A question?
Is one thing that people do they then pick which one is the higher probability, and depending on that, can you just put a static inverter at the end to like switch between, yeah, whichever one's your higher probability?
That's a great question. So the question here is, do people pick different logic style to implement a function depending on what's the switching probability of the gate? And that's exactly what we are going to do. Is actually in the implementation, you will basically have a couple of these design metrics that we introduced very early on in the class. You have to worry about speed. You have to worry about power. Those two are the most important. And then you have also to worry about these signal integrity issues like noise margins and things. And certainly, if you have a lot of switching probability, then you would want to use a gate that basically delivers the same function, but it gives you reduced power. And absolutely, that's what people do all over the place. Basically, even in registers, we will see that basically because the problem here is that although you have reduced capacitance at the output, you really have to look at this gate from like the top level. If you just look at the micro perspective, you're going to overlook a lot of important things. And actually, your question just helped me bring another point up, and that is you have a lot of this capacitance that is hanging off of this node. And then you have to switch this clock node every single cycle, which means that the overhead here is really huge because you're switching not only this capacitance due to pre-charging over every time that you're bringing it up, but you're also switching a huge gate capacitance because you not only have one gate, but this clock signal drives hundreds and thousands of gates. And what people do is a lot of these techniques that reduce activity, for example, in registers, you will find also logic styles that do, for example, speculative computing and sort of look ahead. They say, well, my register is clocked all the time, and that's a lot of overhead. I don't want to do that. So let me speculatively look if my new incoming data signal is different from what I already have stored at the output. And they say then basically only in that case I'm going to accept the clock to flip the state. Otherwise, it's too much overhead, and certainly that's one of the good things to do. Question?
So is this clock frequency equal to the clock of the chip or the entire circuit, or this is some different clock?
That's a great question. It's normally the same clock as for the chip level clock. Okay. So let's just briefly review these characteristics on this slide. So we basically always, this is the standard story basically. Next time if I introduce another logic family, you do the same analysis. You would be able to teach the lecture for me because basically we're looking at the same set of things. Basically, how much does it take to implement in terms of area? That's given here. Then you analyze DC characteristics, try to figure out the noise robustness, and then you finally look at the speed and loading conditions for this gate and power consumption. So now let's list some more issues with dynamic gates that add up to what we already listed. And there is actually four things that we really need to consider. We know that this voltage is established at very high impedance nodes, so you have actually a lot of charge leakage by basically just setting that node floating. And we also have other detrimental effects that we're going to talk about: charge sharing, capacitive coupling, and clock feed-through. So let me go through each of those. And so the first issue is this charge sharing, and let me do this example over here using overhead. So let's look at our dynamic inverter. So we have this evaluation, then we have this pre-charge, this is out. And this is the capacitance that we are interested in. So this is our signal A, this is clock, this is also clock over here. So now we really need to look into second order effects now that we understand what's going on. So some of the second order effects include basically parasitic elements. And looking at the output, what's going to happen is you have, first of all, you have these junction diodes, reverse biased PN junctions between drain and bulk of this NMOS, and this goes down to ground. And you have also another diode that is going up between drain and bulk of this PMOS, and that is going to VDD. Okay, so those are two parasitic elements. And so second order effects obviously include charge leakage that goes from this load capacitance through this diode, but you also have some leakage from sub-threshold conduction of this transistor. So two effects that combine together that will basically take away the charge. If you are in evaluation mode and you still want to stay at 1, that's not going to happen because you will have charge leakage. Now the situation isn't that bad because you have also leakage from the PMOS devices. So you have this leakage from this diode and also sub-threshold conduction of this guy that sort of help you a little bit because that can feed these hungry guys down there that are trying to steal away your charge. But the thing is that you normally size this transistor much smaller than the pull-down devices, and still the pull-down group wins. So overall, when you combine these two effects, you still have charge going down this way. And what that is going to do to your gate is basically when you are in this evaluate phase, then your output will start to degrade. Your high VOH is going to degrade. And I have illustration for that in the slides if we switch back. So basically, once you pre-charge your device, then during the evaluation, due to this leakage problem, your VOH is going to go down. And by the way, that's one of the reasons why this logic works as it does, because you need to periodically refresh this charge and say, well, I need more charge there to establish keep my logic 1 at the high level. So now this is one way you can solve this problem. That's basically the same approach that you had in past transistor logic. You add this bleeder device, and this keeper device now will help you establish voltage level at the output, and I'll just quickly illustrate that over here. So when you have this situation, then the problem is in your evaluation phase when this voltage has to stay at 1. So one thing you can do is basically just put very weak transistor in parallel here that will provide sort of low impedance path to VDD, but this is a better way to do it when you basically have this device. So this is 0, then this one is turned on, and it will give you a good logic 1. When this one pulls down, goes to 0, then as soon as you reach the trip point of this inverter, this guy is going to turn off and it's not going to bother your pull down. So the penalty that you pay here obviously is you have some static power consumption that is occurring during the pull down because you have a fight between this bleeder device, also called keeper, and you have this pull down. So for that reason, it is always also a good idea to skew this inverter in a sense that you're trying to reach this trip point sooner. And in order to turn this guy off, what you need to do is you have to have really strong pull-up. So pull-up means that the PMOS should be stronger, and NMOS should be weaker. So this is called skewed gate. Okay. Questions? Yes? That is just a static CMOS inverter, correct. That's a very valid question. Practically speaking, this is sort of a mix of dynamic and static, and that's what you're always trying to do. Basically, combine the good properties of each of these styles such that you get good implementations. You always have to do some fixes to improve properties of your gates, but you're totally right. This is a mix of static and dynamic, but it's still called dynamic because it's predominantly dynamic computation. Okay. So there is another issue over here is that is charge sharing. And what happens here is that let's assume the case that we have this capacitance charged up during the pre-charge. And let's assume that all of these other capacitances are discharged. So what's going to happen here is that you are going to expose a lot of these internal capacitance to the output. So again, we are following the same methodology here, just analyzing different effects. So basically, methodology here is analyze the second order effects, see what's going to happen with these like parasitic capacitances that you really didn't take into account at the top level. So what's going to happen is that the charge that is stored originally on CL is going to get redistributed. And although your pull down path is still disabled and you are still trying to keep logic 1 at the output, then this guy is going to hurt you because you are creating a conductive path between your useful charge and this internal parasitic capacitance. And that's what's going to reduce your output swing. So let me now consider two cases and I'll derive what's going on here. So we are analyzing a case of dynamic gate that is initially pre-charged to 1, and we look into this pull-down network. That has the signals A and B, and what we're really interested to see is what is the impact of this parasitic capacitance. And again, following the same color code, red is bad. So this is your capacitance CA over here. So let's now assume that B is equal to 0 and that this capacitance was initially discharged. And now that A input goes 0 to 1 during evaluation. So what's going to be my equivalent model in this case is the following. So I really need to look into this. So this will be my A input. So this is the evaluation phase over here. I have my output, This is the load capacitance, and finally I have this parasitic capacitance. So now what is the initial condition is that I have certain amount of charge initially stored on this load capacitance. So the amount of charge I have is CL times VDD. And now that charge is going to get redistributed in this case. So what we need to do now is analyze really two cases depending on operation regime of this transistor. So this one is now at VDD, and what we know is that at the DC state where all the transients have settled, there is no current through the capacitances, right? So that makes sense. So, and now we will have to see what are the bias conditions on this transistor in these two cases. So let's analyze first the simpler case. So let's analyze the case where we have that delta V out is greater than Vt of this device. So if delta V out is greater than Vt, what does this mean basically? Which regime of operation is this device in? If I have my VGS over here, that is VDD minus Vs, and I have VDS that is basically something that is at least one threshold drop below that. So I have basically my VG is at VDD, and then I have my drain voltage, that is, if this is VTN, my drain voltage is over here, VD. So what I have is basically that my VGS, and I have a common source terminal over here. So what I have is that my VGS minus VT is greater than VDS. So VDS is minimum. That means this device is in linear region, right? So everybody agree with that? Makes sense. So this one is in linear region, but now since the current is equal to 0, that means that this device is really at the edge of linear region and cutoff. And the only way you can make a linear region device current equal to 0, in another way to look at this is that to make this VDS is equal to 0. So now in this case I have that my equivalent model reduces to the following. So I have my CL, and then I have also the CA. But I still have the same amount of charge. And in this case, I have basically, I started with VDD times CL. That is the same amount of charge that I have at CL plus CA times my output voltage is now equal to VDD minus delta V out, right? So now I can shuffle these equations, and then I have basically that I have CA times VDD is equal negative delta V out times CL plus CA, and then I end up with this delta V out is equal to negative CA over CA plus CL times VDD. So you can exactly calculate how much voltage drop you have at the output, and this negative sign means that your voltage goes down. So now let's analyze another case when we have delta V out is less than Vt, right? So if this is the case, then the operation mode of my transistor will be saturation and cutoff, because the current has to be equal to 0. So what I have in this case is the following. I have this one at VDD. I have this one at V out. This is CL. And I have the CA. So now what is the voltage over here? If this one is edge of saturation and cutoff. So basically this voltage over here is VDD minus VT, correct? And you basically follow the same approach. You have that your total capacitance is equal CL times VDD. That is equal now CL times V out plus CA times the charge stored on this capacitance, which is VDD minus VTN. That also depends on this value, but let's ignore body effect for the moment. So now you know that your delta V out, just as before, is equal to VDD minus V out, and we can calculate that this delta V out is equal to minus CA over CL times VDD minus VTN. So what this tells you is basically when you compare these two equations is that by adjusting the sizes of these pull-down transistors and load capacitance, you can pretty much predict, you can control how much delta V out you're going to have due to charge sharing. And this may also lead you to some decisions about reordering the devices depending on signal statistics and things like that. So these are all the options that you have available to play with when you're trying to optimize your devices at the logic level. Question?
So if I don't know the value of delta V out, initially how do I know whether it's greater than VTN or less than VTN? Because the value is derived after making that assumption.
Correct. So the question is, if I don't know delta V out, how do I know which formula to use? So that is basically we are again. So we are using the principle here of making an assumption, carrying it through, see if it works. And in this case, so your question is if I calculate these values, how do I know which one is going to play out? And that's a good question. So that's what you don't know, but you have to basically take the worst case. I would take the worst case between these two and then do the simulation, see which one works out. But the values that you derive here is basically just to provide you the understanding of the parameters that you need to tune in reality for simulation to improve this effect. And that's really all that you do in hand analysis. Just like in project, you have to do some hand analysis to sort of understand what's going on and then see what are the first order effects that you can plug in your simulator to play with this. Because if you just simulate this and then you get some delta V out and say, well, my delta V out is equal to something, what do I do about it? I don't know until I do some analysis here and then see which parameters play. That's a good question. More questions? All right. So let's do one charge sharing example here. So when you do charge sharing analysis, the thing is that you need to figure out first the worst case conditions. And the worst case condition is when you expose the maximum amount of your internal capacitance, parasitic capacitance, to the output. Because let's put all the forces together to contaminate the output capacitance as much as we can. So let's analyze this circuit over here, which is rather complicated, but what we need to do is basically, let's observe here we have output capacitance, 50 femtofarads. So now you have to see all these internal capacitances and see, identify the worst case. So we can go down from output to connect with some of these internal caps through A or A bar. And then we have to figure out the worst case condition. Let's go first through A bar. So at this node, I have already 15 femtofarads sitting at this node. Now let's see, can I collect more going down through the stack? If I go down to this B bar, I can introduce another 10. But if I go through B, I can introduce 15, which is more. So this is basically the worst case. One worst case path goes through A bar, B. So let's see what goes what happens in this case. And you can also have some parasitic capacitance of this node, which we neglect. But this is basically the methodology. You identify worst case. Now, let's start with this node. And we have capacitance of 15 femtofarad over here. And then we go down one level down the stack, collect more. So we have total 30 femtofarads capacitance that we need to store, sort of redistribute charge between that capacitance and the output capacitance. And similar analysis can be done for this other case where you have A, and then you accumulate this 15 femtofarad, and then you also go down this transistor to catch more capacitance. And so in this case, what you have is, if you write down the total capacitance that gets redistributed, so you have 30 femtofarad of our capacitance parasitic, and then we have 50 femtofarad of the load capacitance. Now, you initially had the charge that is equal to CL times VDD, now has to equal CA plus CL times V out. So now V out is equal to CL CA plus CL times VDD, and this is now equal to 50 divided by 30 plus 50 times, if VDD is 2.5 volts, then you get, I think this comes to 1.56 volts. So you have delta V out is negative 0.94. So this is a significant voltage drop in this case. So that's how you calculate this charge sharing to a first order. Everybody clear with this? Okay. So now let's go back to slides. So you can use the same solution for charge redistribution by adding another keeper transistor, which basically just never lets you have all these internal capacitances discharged. And this obviously comes with the cost of increased area and power consumption, because you have to manipulate this keeper transistor, and it's also increased clock load. So that is also a lot of overhead in terms of power consumption. And we have another issue here. And this is all basically arising from the fact that we have high impedance capacitance. Whole slew of problems that we have to be aware of. And so now let's assume the case where we have dynamic NAND in combination with cascaded with static NAND. And this is, as we discussed, common thing to do, to basically combine various logic styles in the implementation. So let's assume that our output at the dynamic gate is equal to 1. And let's also assume that output of a static gate is equal to 1. Okay, no surprises so far. So everything works out good, because this one was 0, and this static gate was actually helping this dynamic gate by sort of, let's say, staticizing this node, because it's providing low impedance path to VDD. But what happens if we decide to go a rising transition on one of these inputs? So then these guys kick in. So what this is going to give you is this node will start going down. So output of the static gate will start going down. That will couple through these parasitic capacitances to node 1. And as a result, output 1 will also start going down. And since this one goes down, this will eventually turn on this PMOS device, and you won't be able to pull down all the way down with this output 2. You see the loop here. So basically, output 2 starts going down. That couples through to the output 1. which may turn on this PMOS and prevent this output to going down all the way. And this is illustrated here. So when you fire up the clock, that means you enable your evaluation. And then you start evaluating by increasing this input. So you basically have your output 2 goes down, couples capacitively through out 1, turns on this PMOS, and this one never quite goes to 0. And the final issue that I would like to introduce here is this clock feed-through. This is the phenomenon that you've already seen in the static CMOS, especially when you apply a really fast signal at your input. Then you have all this capacitive coupling, and then you have overshoot or undershoot due to these capacitances. So this is basically a simple problem that you have in dynamic gates as well. So you have your clock signal that is always switching, and this clock signal better be good because it provides reference for your design timing, and it has very sharp edges. So this will likely couple through this capacitance to the output. And what happens here is that output can rise above VDD because you couple through this parasitic capacitance and form a capacitive divider between that parasitic capacitance of a gate and the load capacitance. So for the rising transition, you have clock feed through above VDD, and you also have this undershoot. So that is due to parasitic capacitance. Now, what does this tell you in terms of sizing? What happens if you make this pre-charged device really strong, very big? So what does that mean in terms of your clock feed through? You're going to have more of an overshoot or less? Any ideas? More? Most of you think more? Anybody think less? Yes, it is more, because what you do is basically you're dealing with this capacitance ratio over here. So let me just zoom in into the source of a problem. So you have this guy, and then you have this load capacitance, and then you have this pull down. And then you have this parasitic capacitance sitting here that is coupling through this guy. So the larger W you make, this parasitic capacitance is also becoming larger. It also adds a little bit to this load capacitance, but then the relative ratio of this parasitic and load capacitance increases, and as a result you will have more of this overshoot if you keep increasing your W of your pre-charged device. And as a result you will have longer delay because you're overshooting and basically delaying your wavefronts in time when you reach the switching point. Any questions? Okay. And these are, I would say, maybe even third order effects that we don't really need to worry too much about, but things that could happen include, for example, discharge injection. For example, when you do this capacitive feed through, that it may happen that your drain voltage goes up so high that it turns on that parasitic diode that is sitting between the drain and VDD, makes that diode positively biased, forward biased, and then you're injecting some electrons into your substrate, and that's what you don't really want to do. And you have all these other effects that may arise as well, like ground bounce from supply noise and things like that, but those are less important to worry about, but should still be aware of that. So now the next logical step would be to see how you can build more complex gates with this dynamic logic. And the natural question is, how do you cascade dynamic gates? So now we know that in dynamic gates we can only make transition from 1 to 0 in the evaluation phase. So now let's see what happens if we have cascade of 2 gates, like in this case. So let's assume that we pre-charged our both outputs, out 1 and out 2, And now we are entering the evaluation phase by raising this clock up to high. So now let's assume that our input was at logic 1. So as soon as we fire up the clock at this edge, we start discharging the first output. Okay? So now, since this first output is discharging, what this means is that the quality of logic 1 at this node, at the input of this pull down of the second stage, is getting worse and worse because the output is declining slowly. And what is this going to give you is basically that the output 2 will start also discharging, but at a much slower rate, because at the input of the first gate you have full VDD level. But at the input of the second gate, your logic 1 is slowly degrading, and as soon as you hit VDD minus VT, as soon as you hit the VT actually of this guy, then this pull down turns off, and this logic level stays at somewhere in the middle between 0 and VDD. And that's what you don't want to do. That is really bad. So what this tells you is basically that only 0 to 1 transitions are allowed at inputs. If you have your input, as illustrated in this case, going from 1 to 0, that's not good. And that is something that you need to keep in mind with these dynamic gates. So now that becomes a problem. And then people thought about this and figured out the ways to solve this problem by introducing modifications to this dynamic gates, and a couple logic families arose from that problem. Basically, trying to solve a problem, you introduce more gates that you have to play with. So now, what's one of the ways to do this is using this domino logic. So the property of this domino logic is that you basically have the same dynamic logic, and you just put this inverter in between, as Christina pointed out a moment ago. You basically just put more like a help from static gates, and what this is going to give you is, let's assume that you have 0 to 1 transition at the input of the pull-down network of the first stage. If this node was pre-charged, that means this one was 0, so that's good. So now if you're pulling this down, this 0 goes from 0 to 1, and everything is consistent. So everything works out nicely. You have pull-down node. So here is an illustration. If you have the pre-charge phase, in the pre-charge, you always end up with the final value of 1 at this node. And what's that going to give you in terms of input to the pull-down network? That is going to give you logic 0 here. So when you do evaluation, you can only make a 1-0 transition over here at this node, which will translate into 0 to 1 transition over here. So you no longer have a problem. And you basically have the solution for your problem. You have only 0 to 1 transitions during evaluation, and this is like a falling dominoes, basically. You fire up 0 to 1 transition at the input of one stage, then that goes, output of that stage goes 1, 0, followed by an inverter gives you another domino, basically, 0 to 1, then propagate to the next stage, and so on. It's like falling dominoes. So that's basically where the name came from. So you basically have first stage that engages the second stage, and third stage, and so on down the chain. Questions? Okay. Unlike complementary static CMOS, where we were able only to implement complementary functions, NAND, NOR, and so on, in domino logic we can only implement non-inverting functions. So now we have another toy to play with here. If you need inverting or non-inverting, you have to make decisions what's going on. But this is actually also sort of like the same strategy that we had in CMOS. We had basically inverting function. We had to add this extra inverter because of this cascading problem. So it's basically that inverter is already included there. And this nominal logic gives you very small switched capacitance in the output, and as a result you have very high speed. So if you want to go for speed, use dynamic gates. If you want to go for power, use static gates, but you sacrifice some speed. So there is a trade-off basically. If you look at this power delay plane, if this is my power, this is the delay, then static gates would be here and dynamic gates would be here. So depending what your requirements are, you would be able to select one of the logic styles that fit your specs. And this is what we are going to do actually with the arithmetic blocks. You will see now that this material is going to be much more interesting now that we understand what are the various options that we have available to construct more complicated functions such as adders in the next lecture that we are going to see. Now, another way you can explain the higher performance of these dynamic gates if you look at the logical effort. Let's do an example of a logical effort of a dynamic gate. So let's see, we have this clock over here. And let's do a NAND gate. So we have another clock, we have A, and we have B. So now what's the sizing that will give you the same pull-down capacitance as a pull-down resistance as a unit inverter? Serial devices multiply. So this is 3, 3, 3. And input capacitance to the node A or B is equal to 3. So therefore logical effort is equal to 1. Because the input capacitance of a unit inverter was also 3. If you look at the static CMOS case, we had basically 2, 2, and then we had 2 PMOSs that were also 2. So in a static CMOS case, we had 4/3. So since you have lower logical effort, that means you have higher speed. Just an exercise. Questions? Okay. So everybody copy this? Okay, so let's go back to slides to see what else we can do with these gates. One of the ideas is that every time we have this inverter in between, that basically ensures that we always have logic 0 at one of these pull-down guys. And that gives you the idea to basically eliminate this conditional evaluation device, because you're all set, because in the pre-charge, assuming that the inputs to the pull-down network come from other domino gates, all the inputs will be 0. And then once you evaluate, you can only have 0 to 1 transition, and basically everything is consistent. If all your inputs are 0, that means you have no pull-down whatsoever. And then when you release the clock and basically no longer do pre-charge, then in the evaluation phase you can only basically pull down. So you don't need that conditional device, right? Because there is no contention with the pull-up. But that works okay. That idea is nice, but then there is also a problem. Anybody see what's the problem? So the problem now is in pre-charge, because what happens is that your pre-charge is now going to ripple through, because what happens here is that if you assume that you need to pre-charge, and this one was at logic 0, that means that you have 0 to 1 transition over here, followed by 1 to 0 transition, in which case you're turning off the pull down of this guy so that this one can pre-charge. So you're basically delaying your pre-charge operation in time. As you go down the chain, you're pre-charging the first one, second one, third one, and so on. And just like a little thought experiment here, if you are to minimize the power consumption of these gates, how would you size the gates down the chain to minimize the power? If you have this situation, so you have basically stage 1, stage 2, stage 3, and then this one has basically, this one is pre-charging, this one is pre-charging, and this one has static power consumption because the pull down hasn't still been disabled. But this one is trying to pre-charge, but it can't because it's fighting the pull down branch. And this one is also pre-charging. And then you have basically this pre-charge delay in time. So now if you have W1, W2, W3, how would you size these W's relative to each other to minimize power consumption? W3 is smallest, correct, because it spends the most of the time dissipating power. So you understand the type of trade-offs you can make. So that's how you can minimize this static power consumption. W3 should be smallest. That's correct, thanks. Just checking if you're following. Still awake. All right, so that is pretty much about dynamic gates. I have maybe one or two more slides to show you next time, but that's pretty much all you need to know about dynamic gates. And I guess I'll see you later today in the lab, and have a good weekend.